Yeah, so the first talk of this session is mild asymmetric message franking, illegal message only and retrospective content moderation. The talk will be given by Yijan Zhang. Yijan, please, over to you.
Thank you for the introduction. I'm Yijan Zhang, coming from University of Wollongong. Today I will be delivering a presentation about the topic mild asymmetric message franking, illegal message only and retrospective content moderation. I'm presenting on behalf of the authors of this paper. They are very sorry to be unable to attend the conference in person. So let's start. Oh. So here we start from the background or the motivation of this research. Our background is the message applications. In these platforms, we usually adopt end-to-end encryption to ensure the message privacy. But the widespread adoption of HOE encryption will cause a tension between user privacy and moderation. Concretely, these platforms are usually misused for spreading malicious information like harassment messages, phishing links, and fake news. However, end-to-end encryption stops the law enforcement and the national security community from checking these illegal messages. So our goal is to find a balance between user privacy and moderation. Oh.
It's only like you have to like this.
Okay. Oh yeah. So approach is to carry out a message franking. This primitive can be integrated to end-to-end encryption. So for in this framework, MAF empowers the receiver Bob with the ability to report the received illegal messages to a moderator. This reported message includes the sender's identity and the message and some special strings like signatures or hash values. So with all these elements, the moderator can verify whether this illegal reported message originated from the sender or not. Here, if the moderator is different to the platform, it's called a symmetric message franking. So in this primitive, an important property is called deniability. It's that to ensure the confidentiality of sender. So roughly speaking, this property ensures that the sender can deny sending a message when facing public. So for our motivation, the first problem is that Bruce Tucker et al. Has claimed that the deniability is a conflict with unflammability. This flammability ensures that no party in the system can frame an innocent sender of sending an illegal message. But for the AMF construction proposed by Pratyay et al., their construction didn't support unflammability because they support judge receiver compromise deniability. It means when the secret keys of receiver and moderator are compromised, a party can use this case to forge a valid message, so that the receiver and the moderator can accept them. Then our goal is to support both properties simultaneously. So we need to impose a constraint on the receiver and the moderator. We request that no forged message can be accepted by the Bob and the moderator simultaneously. Thus, this curve space out for affirmability. And for second problem, we observe that the moderator in AMF is too powerful. This moderator has the ability to check all messages in platform. So we restrict this moderator to only check illegal messages, will concurrently provide him the capability of retrospective content moderation. Then we go into the contributions. Our main contributions can be summarized as follows. At first, we propose a new primitive, Mulled Symmetric Message Franking, MAMF. And to construct this primitive, we also propose two new building blocks, USPCE and dual HPS KEM sigma. And finally, we gave a generic framework of constructing MAF from these two building blocks. Then we're going to see how this primitive works. For the formal definition, this primitive consists of 11 algorithms. Here, only the first 8 algorithms will be used in system execution, and the last 3 algorithms is just used to deal with special cases. And this system contains 4 rules: sender, receiver, judge or moderator, legislative agency. This agency is just responsible for the set of illegal messages. And let's see how this system works. First, all these properties will run their key generation algorithm to generate their public key and secret key. But here, legislative agency will initialize a set of illegal messages and embed this set into his output from key generation algorithm. Then the sender will run blank algorithm to generate a signature regarding his message. After receiving this signature and the message, the receiver will verify whether this message is legal. And if this is the case, he will report this illegal message to the judge. And we note that if this illegal message is a newly joined one, then the legislative agency must use his secret key to generate a token for this judge, so that the judge can verify whether this reported message is illegal. Then this is the other 3 algorithms. They are only designed for the case when the secret keys are compromised. So here we present a security comparison between AMF and our MAMF. Here, MAF will achieve additional two properties: untraceability and confidentiality of sets. Next, I will introduce all these security properties one by one. First, unforgeability is the fundamental property of MAMF. It's very simple. The receiver cannot be deceived into accepting a message not ingenuinely sent by the sender. And accountability ensures the functionality of reporting illegal messages. It has two types, sender binding and receiver binding. For sender binding, it ensures the sender cannot trick the receiver into accepting unreportable messages. Similarly, for receiver binding, the receiver cannot deceive the judge to frame an innocent sender. The next one is deniability. Just as I mentioned earlier, it has three types, corresponds to different cases when the secret case of sender, receiver, and judge are compromised. And frameability is just no party, even given the secret case from receiver and judge, is able to produce a signature acceptable to both these parties. So we additionally consider traceability. It aims at both parties, legislative agency and the judge. For this agency, it cannot determine whether someone has actually sent a message. No matter this message is not, no matter whether this message is in the set. And for judge, without the assistance of the agency, because this agency will provide the token to this judge. So without this token, the moderator cannot ascertain the sender's identity if this message is not in the set. At last, the property is confidentially set. It's also simple. The public case will not disclose any information of the set of illegal messages. So let's go into the MAF construction. Before introducing this construction, we need to introduce two building blocks. The first one is USPCE. It is generalized from the well-known primitive set by constrained encryption. This primitive is very simple. The key generation algorithm will embed a prefix stacks into a public key and a secret key. And for encryption, it will generate a ciphertext regarding message and element. And the decryption algorithm will recover the message only when this item is in the set. So the functionality of this primitive seems satisfy our requirements, but it is still insufficient because the decryption is infeasible when this item is not in the set. So we propose a new primitive, universal set pre-constrained encryption. It has two additional algorithms. The set algorithm will additionally generate a master secret key, and with this master secret key, it can run token generation algorithm to add this newly joined item and output a token for this. So the correctness will now cover both cases when item is in the set and X is not in the set. Due to the time limitation, I will skip all the security properties. Then we introduce the second building block. It's also generalized a known primitive HPS KEM sigma. It uses to construct a symmetric group messaging franking. It can be seen as a variant of key encapsulation mechanism. Here we mainly consider is dual version. First we record the definition of this primitive and then show its dual version. For HPS KEM sigma, its main algorithm consists of several ones. Here, encrypt C and encrypt C star will generate output well-formed ciphertext and ill-formed ciphertext respectively. And the encrypt key algorithm will output an encapsulated key. The decrypt algorithm will help us to recover this encapsulated key from the ciphertext. So this is the correctness, and we also request that there are other algorithms to help us to check whether keys and ciphertext are well formed or not. Then we also require this primitive to support a Sigma protocol for their three relations. The first two relations is just for proving the keys and the ciphertext are generated normally. And the second, the last relation is for as ciphertext is ill-formed. Then this is our dual version of this primitive has these four additional algorithms. Most of them is similar to original ones. Just takes as a tag as the input additionally. And it also requires that there exists a Sigma protocol for three relations. They are just the dual version. So here we have, because we propose a new primitive of dual HPS KM sigma, it also has some new properties. Here, due to the time constraint, I will just introduce smoothness. Smoothness requires that given an ill-formed ciphertext, the decayable algorithm will output a key that seems uniformly over the key space, and so an extended smoothness is just a dual version of this property. So we can use this property to prove the deniability of our MAMF. Finally, going to the framework of MAF. Here for the setup algorithm and the key generation algorithm from other parties, it mainly invokes the setup algorithm and key generation algorithm from dual HPS KM sigma and US PCE. Here, note that for this key generation algorithm for agency, it will run the setup algorithm of US PCE so that they can embed the set of illegal message into the parameters. Then the Frank algorithm seems a little complex. It first to generate a well-formed ciphertext from dual HPS KM sigma, and also two encapsulated keys from the algorithm in KM sigma, and then it will generate a ciphertext using the encryption algorithm from US PCE. And finally, it will generate an IZK proof for some relation. This relation we will explain later. The verification algorithm is very simple. First, it verifies this proof is valid or not, and then using the decayable algorithm to check whether the encapsulated key is recovered correctly. And the token generation algorithm is just as in USPCE. For the judge algorithm, it is similar to verification algorithm. A difference is that this algorithm will first decrypt the ciphertext to recover the tag, and then use this tag to check whether encapsulated keys in dual HPS KM sigma is recovered correctly. So other three forge algorithm is similar to Frank algorithm, but a difference is that they will generate an ill-formed ciphertext, and for different algorithms they will generate different keys. So finally, we introduce this let's say it's the analytic relation. It is related to our security proof. It mainly has three parts. The first part, part A1 and A2. This thing, it ensures that the sender's secret key is known, and the ciphertext and the keys are generated just as in the Frank algorithm. So this part guarantees accountability. And the second part is A3 and A4. It aims at the fact that the ciphertext is ill-formed, and the key is obtained from this algorithm. So it provides universal and judge compromise deniability. The second part is A3 and V4. It's similar, but provides receiver compromise deniability. Here for both second part and the three part ensures unflammability, and all these parts is guarantees unforgeability because the signature would be accepted by the receiver and judge only when it's generated from the Frank algorithm. Finally, traceability and confidentiality of set are trivially implied by the underlying USPCE. So this is a summary of our construction. For more details, please refer to the paper. This is all my presentation. Thank you for your attention.
Thank you. Would you take questions because you are presenting on behalf of them?
Yeah.
Is it okay if you take questions as well?
Maybe it's not.
Okay, that's fine. So if you have any question, just contact the authors. All right. Thank you. So the next talk is constrained pseudorandom functions for inner product predictions from weaker assumptions. The talk will be given by Sacha Sarvan-Schreiber. Sorry for mispronunciation.
Thank you. My name is Sasha, and I'll be presenting new ways of building constrained PRFs. The overview of the talk is going to be some background on PRFs and constrained PRFs, a secret sharing perspective on constrained PRFs, which will form the basis of the framework, our framework and instantiations, and then an evaluation of some of the constructions, and I'll conclude with open problems. So what are constrained PRFs? Well, let's first understand what a standard PRF is. So a PRF is a function that informally has to look pseudorandom when evaluated on some input. And the way this is modeled is with a challenger that in a setup phase will sample some PRF key K, then sample a random function, and sample a bit D. After which, a distinguisher is going to query this challenger on some inputs xi, and the challenger based on the bit B will either respond with the function evaluated using the key K or the random function evaluation. And it will respond to the distinguisher with this value. And the PRF is secure if the distinguisher cannot guess the value of B. So constrained PRFs are pseudorandom functions that have an additional constrained functionality that allows us to take a master PRF key and constrain it with respect to some predicate C to derive a constrained key. And informally, what this has to satisfy is that the constrained key can be used to evaluate the PRF on all inputs x where the constraint is satisfied, so all valid inputs to the PRF. And we will define this constraint as a circuit where on an input x, if the circuit the predicate outputs 0, then we will say the constraint key is authorized on that input. And if it outputs 1, we will say it's unauthorized. And so the correctness property will say that if the constraint is 0, so satisfied, then the PRF evaluated on the master key will equal the PRF evaluated on the constraint key. And we still need pseudorandomness, which says that the master key evaluation on all inputs that do not satisfy the predicate, all unauthorized inputs, should still look pseudorandom even given the constraint key. And then finally, we can consider a third property, which is hiding, which just says that the predicate itself has to remain hidden even given the constraint key. And so our focus in this talk is going to be on inner product predicates. The way this looks is we have a circuit C that takes as input X, and we're gonna compute the inner product. And if this inner product is 0, it's authorized. If it's not 0, it will be unauthorized. And so the circuit is parameterized by some vector Z that will be the constraint. And why are we interested in looking at inner product predicates? Well, they can be used to generically build other constraint PRFs for other predicates. So we can build TCNF predicates, bid fixing predicates, and matrix product predicates from CPRFs for inner product predicates. So how does the definition for constraint PRFs work? It's similar to the standard PRF security game. So again, we have a challenger. The challenger will sample a master secret key. It will then sample a random function. The challenger will send a constraint that it wants to be challenged on to the challenger. Using this constraint, the challenger will compute a constrained key that it sends back to the adversary. And then we proceed as before with an interactive query phase where the distinguisher will query the challenger on inputs X and get back either the real PRF evaluation or the random evaluation. And so this was what I just showed was selective security, and we can additionally request choose adaptive security where the adversary gets to first query before committing to the constraint. It's just a slight variation of the original definition. So what do we know currently about constraint PRFs for inner product predicates specifically? So we know first how to build generic constraint PRFs for very complex predicates, so NC1 and all the way to all polynomially computable functions from LWE and IO. And most of these get selective security. We also know how to build constraint PRFs for NC1 from LDDHI, which is the LDDH inversion assumption, in addition to DDH. And if we additionally swap the DDH assumption with the random oracle, we get adaptive security. And these are not constraint hiding. For inner products predicates specifically, we know how to do it from the DCR assumption. This is a recent work from last year. And so the first question is, can we build constraint PRFs from weaker assumptions? So currently we only know how to do it from the DCR assumption for inner products if we only focus on inner products and not more general constraint PRFs. And so the first question was really how can we maybe remove this LDDHI assumption, which is a bit of a strange assumption, and maybe just get something from the random oracle model directly. And so in this work, we show that we can build constraint PRFs from just a random oracle for inner product predicates with adaptive security and constraint hiding. And the natural follow-up question to this is, well, if we can remove the LDDHI assumption for inner product predicates, maybe we can also just get something from DDH. And so in this work, we show that we can actually also build inner product constraint PRFs with selective security from DDH. And then these are structured, or the DDH assumption, DCR assumption are fairly structured assumptions. So a question was that I asked myself was, can we actually do something from unstructured assumptions, such as LPN, for example? And we show a positive result, which is that we can build weak PRFs. So weak PRFs are only pseudorandom on uniformly random inputs from a variable density LPN assumption, which is a variant of LPN. And finally, given that we got all these results, the most natural question is, can we actually build something from just one-way functions? And we partially answer this by showing that it's possible to build a one-way function based constrained PRFs for inner products, but it's limited to only a polynomial domain. So how do we get these results? It all stems from a secret sharing perspective on constrained PRFs. So I'll explain what this means in a second. But the idea is to view the master secret key and the constrained key as being secret shares of a vector z. And the vector z here is going to be the constraint. So if we have two parties, Alice and Bob, the idea is we can define a secret sharing of the vector z as being two uniformly random shares, or z0 and z1, that combine to subtract to z. And so the idea is to basically define the master secret key as being Alice's share of z, and Bob's secret key, or constraint key, to be Bob's share of z. And the thing to note here is that because one of these keys, specifically z0, or Alice's share, can be sampled independently of the constraint, and then we can reverse sample Bob's share once the constraint z is known. Then for an input x, what we can do is first derive a key k by taking the inner product between the share and the input x. And the property that these two keys, ka and kb, satisfy is that the inner product between them will be, they will form shares of the inner product between z and x, and z is the constraint. So the idea is, like, when the inner product is 0, the two keys will be equal by properties of subtractive sharing. And so then we can use these keys, the idea at least is to use these keys and evaluate a PRF on input x using this derived key. Okay, so with this kind of general idea, we can now construct a constrained PRF. So the first attempt is to define the master secret key as being just the share z0, or uniformly random vector z0. And then for a constraint vector z, once we have a constraint z, we can define the constraint key as being z0, the share z0 that we just sampled, minus the constraint vector z. And so now z0 and z1 will form subtractive shares of the constraint z. Then we can define the evaluation algorithm, so the master key evaluation algorithm, as first computing this inner product between the master key and the input, and then outputting the PRF evaluated using the derived key k on input x. And the constraint evaluation algorithm is essentially identical, except it uses the constraint key to derive the key k. And it outputs f evaluated on x. So is this correct? The way to see correctness is when the constraint is satisfied, so z and x, inner product between z and x is 0, or k is satisfied, then the two keys k and computed in the constraint evaluation algorithm and the master evaluation algorithm will be identical. And this is because the purple term here will cancel out, or is 0. But for security, we can't actually show security for this because there's a trivial attack here, which is that given the constraint key, it's easy to recover the master secret key by just adding back the constraint. So because the adversary knows what the constraint vector is, it can trivially just recover the master secret key, which is not good. So a second attempt at this, which we'll prove security for in a second, is a very trivial modification of this construction, which has a sample random scalar delta, and defining the constraint key as being the corresponding share computed by subtracting the master secret key z0 minus delta times the constraint. And so you can think of z0 and z1 now, or the master key and the constraint key, as being secret shares of delta z. And correctness still holds because when the inner product is 0, the delta component cancels out, and so delta times the inner product is still going to be 0. The problem, however, is that and the keys are still going to be highly correlated because the derived key, the constrained key is going to be still correlated to the master secret key derived in the master evaluation algorithm. And so essentially this is not going to necessarily be secure because if we use any PRF here, we're going to be evaluating this PRF on correlated keys, which generically is not going to be secure. But the solution to this is we can use a special type of PRF, or related key attack secure PRF, where this won't be a problem. And so this leads us to a general framework where we're going to use RK secure PRFs to instantiate constrained PRFs. So just a little bit of background on what RK secure PRFs are. If we recall the definition of a regular PRF, we have the security game where the adversary has to guess the bit B after querying the challenger. And the related key attack secure PRF is very similar to this, except now the adversary has a little more power. It gets to send a function phi along with its input, and the response is going to either be a uniformly random function evaluation, or it's going to be the function evaluated with the key derived by applying this function k. Function phi on the key k. And so with this, what we can, the way to see how we can instantiate this framework securely is that the inner product that we computed from the constraint key is really an affine function of this scalar term delta. And this affine function is going to be determined by x, which hopefully will make sense in a second. So if we come back to the master key evaluation algorithm and the constrained evaluation algorithm, if we now have f, the function we use, the PRF we use in the output, be an RK secure PRF, then hopefully now the fact that the keys are related will not be a problem because the PRF will be immunized against this. And so in this reduction, we can quickly see why this would work. So we start with the CPRF security game, where the adversary now has a vector z as its constraint that it sends at the beginning of the game. It gets back this constrained key z1, and then it gets to query the challenger on inputs xi and gets back the function evaluated with the inner product between the xi it sent and the master key z0. So the first step to show security is to swap how we define z0 and z1. We can just define z1 as being uniformly random and reverse sample the master key. This is just a syntactic change. It doesn't change anything about the game. And then the third step, and this is kind of the critical step, is we can define the output, the inner product computed to compute the key k that is used to evaluate the PRF f as being an affine function parameterized by values a and b. So we can replace this inner product in the, I guess the laser doesn't work, but we can replace the inner product as being an affine function of some key delta, where the a and b values are determined by the input x sent by the distinguisher. And once we have that, we don't actually have to sample the key k anymore. We can let that be an RK secure PRF key sampled by another challenger. And we can respond to the adversary's queries by querying our own challenger and responding with the PRF evaluation that our challenger sends back. And so this proves, this will now is identical to the RK security game. And so once we've, so now that we have this framework, we can now instantiate it using different RK secure PRFs for affine function that support affine functions. And so the first instantiation of this is just a PRF in the random oracle model, which allows us to build an RK secure PRF kind of trivially using a random oracle. The second construction is from DDH, and for this we can use the RK secure PRF construction of Abdallah et al. and which they show is secure for affine functions under the DDH assumption. The third construction is from variable density LPN, and this follows from a PRF candidate that was proposed a few years ago. But that PRF candidate is only a weak PRF, which is why our constrained PRF derived from VDLPN is also going to be a weak constrained PRF. And then finally, we show that we can use the RK secure construction of Applebaum and Witter to instantiate our framework. It does require a little more work than just applying their construction for technical reasons, but it gives us an instantiation from one-way functions with a polynomial domain. And it turns out that these two the first two instantiations are actually practical. So we can implement and evaluate them, which is what we did. And our implementation is open source and was reviewed, obtained artifact badges from Asiacrypt. So for the random oracle-based construction, we actually get something that is very fast, even with very long vectors, so long constraint vectors. It only takes roughly 200 microseconds to evaluate the constraint PRF. And the bottleneck here is not really the PRF evaluation, it's computing the inner product between the constraint key, or the master key, and the input. And then from DDH, we also get something that's practical. It's quite a lot slower than the random oracle construction, but it's still on the order of a few hundred milliseconds, even when the vectors get really big. But here, in contrast to the random oracle construction, the exponentiations in the group are what limit performance. And so I'll just conclude with some open questions. The first open question is finding concrete applications for CPRFs with inner product predicates. If you stay around for my next talk, you'll see one application. The second one is extending the constructions from inner products to NC1 constraints. So this will be the obvious next constraint class that we could investigate. The third one is instantiating the framework for more assumptions. So this would require maybe finding new ways of building RK secure PRFs or related key attack secure PRFs, which can then be plugged into this framework. And then a really interesting open question is maybe getting a constraint PRF from just one-way functions, which is a minimal assumption, with a super polynomial domain. So currently the construction is limited to only a polynomial domain, but maybe there's some way to make it work with a super polynomial domain. So that's it. Thanks a lot, and you can find the paper here.
So, questions? All right, I wanted to ask you about the applications, but I think you mentioned the applications already.
Yeah, so my next talk is going to be on one application. Yeah.
Oh, awesome.
Yeah.
So what I wanted to ask about, like, I see like without using like heavy tools like I/O, I mean only adaptive constructions all are based on random oracles, is it true?
No, because there's a one construction from LWE for inner product predicates that supports adaptive.
I see,
Yeah,
I see.
that is adaptive, yeah.
All right, okay, thank you. Thanks for the clarification. All right, then we thank the speaker again. Yeah, so next slide, I guess, yeah. So I guess Shasha will give the next talk as well.
Well, I'm back. So.
Yeah, quite OT, lightweight oblivious transfer with a public key setup. Please go ahead, yeah.
All right, so yeah, one of the open questions in my previous talk was finding a concrete application for CPRFs with inner product predicates, and this talk is going to show one of such applications. And this talk is this is based on joint work with Geoffroy Couteau, Lali Devadas, Srini Devadas, and Alexander Koch. So yeah, the talk is about fast oblivious transfer with a framework we call QuietOT. The overview of the talk is going to be some background on oblivious transfer, background on oblivious transfer extension, the QuietOT framework, and an evaluation of our framework. So what is oblivious transfer? Oblivious transfer is instantiated with two parties, Alice and Bob, where Alice has two messages, M0 and M1, and Bob has a bit B. And the goal is for Bob to obtain M sub B, so one of the two messages Alice has, and Alice must learn nothing, or gets nothing out of the protocol. And so the way this works is Alice is going to input M0, M1 into the OT protocol, Bob is going to input his bit B, and out of this protocol, Bob will learn M sub B. Oblivious transfer is a fundamental component of secure computation. So in secure computation, instead of having, Alice might have an input X and Bob might have an input Y. And the goal there is very similar to oblivious transfer, except now Bob needs to learn a function of f of xy. Under the hood of some secure computation protocols, Alice and Bob need to run a lot of OT instances. So they have to run a lot of oblivious transfer protocols in parallel. And each of these OTs is typically very computationally expensive. It requires public key operations. So the idea introduced by Beaver in '96 and IKMP in 2003 is to first compute a few oblivious transfers that might be expensive, and then extend them into many oblivious transfers that are fairly cheap to evaluate. So in particular, the first few oblivious transfers might be require public key operations, but then extending those oblivious transfers into more oblivious transfers is going to be cheap, and in particular only require using symmetric key operations. Cool. So in a little more detail, oblivious transfer extension is going to have Alice and Bob run a few OT protocols. And after these OT protocols complete, they can then extend them into many pseudorandom OT correlations. And so what this looks like is Alice is going to obtain some pseudorandom bits A0 and A1, and Bob will obtain one of the two A's generated by Alice, along with the bit indicating which one he obtained. And then they can extend these into as many pseudorandom OT correlations as they need. With OT extension, there's typically this initial few OTs that have to be performed, but with a public key setup, we can push the kind of non-interactive nature of this protocol to the limit by having Alice and Bob just swap public keys instead of having to perform OTs. And using these, once they have these public keys, then they can locally generate many pseudorandom OT correlations. And so you can think of this a little, the parties can post these keys to a public bulletin board and don't necessarily have to be online at the time to exchange these keys. And so you can think of this as being similar to like a Diffie-Hellman key exchange, where instead of obtaining a key at the end, they obtain material that allows them to locally derive many OT correlations. So this is going to be what we're going to try and build with QuietOT. And in QuietOT, the communication model is going to be exactly that. Alice and Bob will generate public keys that they exchange. And from these keys, they will derive some local correlated keys that are going to be small. And there should be some extend algorithm that can be run by Alice and Bob respectively that then generates the respective OT correlation for each party. So the way we're going to build this requires three ingredients. The first is going to be a constrained PRF for inner products. The second one is a non-interactive vector OLE, which I'll explain later. And then the third component that we need is a weak PRF candidate. And when all of these are taken together, we obtain quiet OT. So first, let's see what a constrained PRF for inner product predicate is. So a CPRF, as I mentioned in the last talk, for those of you who are here, can have, you can take a master PRF key, constrain it on some circuit C, and obtain a constrained key from the master key. And the property we want is that we can evaluate the PRF with a constrained key on all inputs that satisfy the predicate. And so in the general case, we have the constraint be any circuit that outputs 0 or 1, and it's going to be authorized if the value is 0 and unauthorized if the value is 1. And then for correctness, we want, again, that the PRF evaluations are equal when the circuit outputs 0, and when the circuit outputs something non-zero, the PRF evaluation under the master key should be pseudo-random. And here we will not necessarily need hiding. And so unlike in the previous talk, we don't care about hiding here. So for efficiency, we want to use a constrained PRF for inner product predicates, which I just showed you was blazingly fast in practice. And so here, the idea is that we're just going to have the constraint circuit be an inner product between the input X and the constraint Z. And this is going to now be defined over some ring R. And for efficiency, we're going to use the random oracle-based constrained PRF that I described in the previous talk. So using this building block, the next building block we need is a weak PRF candidate. And specifically, we need an inner product membership PRF, which is a special type of PRF that can be instantiated using the BIPSW weak PRF candidate. And the BIPSW weak PRF candidate has this form where the secret key of the PRF is a vector k. And to evaluate the PRF, you first take the inner product between the input X and K. You take that modulo 6, and then you round the result to a bit, 0, 1. So this is exactly the PRF candidate described in BIPSW 18. And the nice thing about this PRF is that the evaluation is just an inner product that we then round to a bit. However, the thing to note here is that the evaluation of this PRF cannot be evaluated as an inner product because the rounding step is nonlinear. And so this is why, this is where this inner product membership property comes in, which is that we can view the evaluation of this nonlinear PRF as falling into two sets. So specifically, if the PRF evaluates to 0, then we know that the inner product between K and the input X, modulo 6, is going to be in the set 0, 1, 2, because that's the definition of rounding. And if the PRF evaluates to 1, we know that the inner product mod 6 is going to be in the set 3, 4, 5. Okay, and so this is why we know that it's, if the inner product is a member of one of these two sets, we know exactly what the output of the weak PRF is going to be. Okay. So I'll describe later what this non-interactive vector OLE component does, because that's involved only in the public key setup. And for now, with just these two building blocks, we can kind of see how quiet OT can be instantiated. So if we put these two blocks together, the main idea is to use something that was exploited in previous work on OT extension, which is to take this constraint predicate and define the constraint predicate as being itself a PRF evaluation. So this might look a little strange, but what we're doing is we're defining the constraint predicate as itself being a PRF evaluation. And so what this means is that a pseudorandom subset of the constraint PRF is going to be constrained for this constraint key sk sub c. So to visualize this a bit better, like we said before, if the constraint predicate is 0, we say it's authorized. If it's 1, it's unauthorized. So if the PRF, this little PRF with key k evaluates to 0, then the constraint key is going to get the same value as the master key. But if the PRF evaluates to 1, then the constraint key is going to be pseudorandom, produce a value that's pseudorandom with respect to the master key, and so on and so forth. So basically all we did is we took this constraint predicate and we just made it itself be a PRF. And so the idea is to, one of the ideas we use is to instantiate this with the BIPSW weak PRF that I just described before, which is going to be an inner product and rounded to 2. Now, like I mentioned before, we want to use a constraint PRF for inner products, but this is not an inner product, so we can't evaluate this BIPSW PRF inside the constraint predicate, an inner product constraint predicate. It's just not powerful enough. But the core idea in QuietOT is that we actually don't need to do this. Well, all we need to do is use many constraint PRFs. And so this, bear with me, and this will hopefully make sense in the next slide. So now, using just a constraint PRF for inner products and the BIPSW weak PRF, I'll show you how to build an OT extension. For now, we are going to be okay with the trusted setup. We'll later remove this with a public key setup. In the trusted setup, we're going to first sample BIPSW weak PRF key k, and we're going to generate a master constrained PRF key that we're then going to constrain to this constraint class that's going to be in the inner product between the BIPSW key k and the input x, mod 6. And so whenever the inner product is going to be 0, this circuit is going to output 0, which means that the constraint key sk sub 0 will get the same value as the PRF evaluated on the master key. And then we're going to do this again. But now we're going to change the constraint predicate to only be satisfied when the inner product is 1. And because there are 6 possible values for the BIPSW inner product, we're going to generate 6 master keys and 6 constraint keys. Where each constraint key is going to correspond to 1 possible inner product value, 0, 1, 2, 3, 4, 5. Okay? And the trusted setup is going to output to Bob the 6 constraint keys, and along with the BIPSW weak PRF key. And LS will get the 6 master keys. So just to look at everything that the 2 parties get. So Bob gets the BIPSW weak PRF key. He also gets the 6 constraint keys that correspond to each possible inner product value. And Alice just gets all the constrained master keys, or the master keys for the constraint PRF. Yes, and so each of these constraint keys is going to correspond to 1 value, 1 possible inner product value. Okay. So now for a public random input x, and the reason it's random is because we're using a weak PRF for the in the constraint predicate. Alice can generate 6 values. She can evaluate the constraint PRF using the master key, using all 6 of her master secret keys on the same input x, and that gives her a total of 6 pseudorandom values. And Bob, he has the key, the BIPSW key k. He can figure out what the inner product value is by taking the inner product between x and k. And so in this case, it's 4. And what this means is that Bob can use the fourth constraint key, which will derive the same value a sub 4 that Alice obtains. And the reason this works is because the inner product was 4, which means that the fourth constraint key that Bob received is only going to be authorized when the inner product is 4, which means that Alice obtains the same, Bob obtains the same value computed by Alice with the fourth master key. However, the important thing to note here is that Bob does not get cannot compute any of the other 5 values computed by Alice, since the predicate will not be satisfied for the other 5 keys. And so this, if the inner product was instead 1, the same thing applies. Now Bob can compute a sub 1, but he cannot compute any of the other values. And so on and so forth. Inner product 2, Bob can compute a sub 2, but he cannot compute any of the other 5 values. Okay. So it turns out that this is enough to instantiate what's known as random bit OT. And then we can apply a transformation to get chosen bit OT. So in a random bit OT, Bob does not get to choose his bit B. The bit B is going to be determined pseudo-randomly. But he must still obtain one of the 2 messages that Alice holds. And so the idea is that Alice and Bob now have these values that were computed with the CPRF as I explained in the previous slide. And so now Alice can mask her inputs, M0 and M1, using the first 3 values computed A0 through A2, and the last 3 values to mask M1. And Bob, he only has one value in one of the 2 lists computed by Alice, and so he can recover one of the 2 messages, but not the other one. So in particular, if Bob has A2, he can recover M0 by unmasking A2, or if he, for example, had A3, he can unmask M1 using A3 that he obtained from the constrained PRF. So now that scheme requires oblivious transfers to instantiate, because I said like we have this trusted setup process. And so how can we generate this with a public key setup? So we want to replace this trusted setup with just a non-interactive setup that allows Alice and Bob to generate these master keys and constraint keys on the fly. And so this is where non-interactive vector OLE comes in. The idea is to use the construction from the previous talk, where the important thing to focus on is just the definition of the constraint key and the definition of the master key. And so because we can think of the constraint key and master key as being secret shares of delta times k, or k is the constraint, we can use a non-interactive vector OLE protocol where Alice inputs a scalar delta, and Bob inputs his BIPSW weak PRF key k. And from this non-interactive vector OLE protocol, they obtain secret shares, subtractive secret shares of delta times k. And so they can automatically just use Z0 and Z1 as being the master key and constraint key, respectively. And so this gives us a non-interactive setup. Non-interactive vector OLE, though I didn't describe it in detail, was previously known from group-based assumptions. And in this paper, we give the first ring LWE construction for non-interactive vector OLE, which makes the quiet OT post-quantum secure, plausibly post-quantum secure. So now we implemented and evaluated quiet OT. Again, the implementation is open source, and we received artifact evaluation badges from Asiacrypt. So previous constructions, the state of the art for OT extension is soft-spoken OT, which gives us reasonable communication overhead. The communication overhead is tunable, but it gives us a lot of OTs per second, so roughly 45 million OTs per second in computationally. And we can reduce the communication overhead for OT, but that comes at a cost of increasing computational overhead. There are other protocols for OT extension, namely RRT, that gives us optimal communication of 3 bits per oblivious transfer and pretty reasonable computational performance. And then if you went to the talk on Tuesday on foliage, that gives us even better performance of roughly 25 million OTs at 3 bits per OT. But the thing is, none of these constructions offer a public key setup. So if we look at what can we do with a public key setup, the answer is, well, from 2021, we knew how to get 1 bit per second, 1 OT per second at 3 bits per OT. And then very recently, this was improved quite substantially to roughly 12,000 OTs per second. And with quiet OT, however, we can get much, much better throughput of roughly 500,000 OTs per second by just modestly increasing the communication to 7 bits per OT. And if we additionally introduce AVX, then we can get almost 1.2 million OTs per second at the same communication overhead. Now you might notice here the public keys are somewhat bigger. And this is because we're using ring LWE for the non-attractive vector OLE. If we instead used group-based assumptions, we'd have similar public key sizes as the previous construction. And just for context, while this might look big, the average web page size in 2024 is 2 megabytes. So there's a lot I couldn't talk about, but please check out the paper. And I'll just leave you with 2 open questions. The first one is getting malicious security for the protocol. And the second one is, can we reach the throughput of classical OT extension protocols, but with a public key setup? Thank you.
Thank you. Questions? Yeah.
I'm wondering whether it is possible to construct PIR from your from CPRF and weak PIR together.
So you're saying, can we construct quiet OT from a weak constrained PRF and a weak PRF?
Yeah.
We do discuss that in paper. It is possible. There are some technical issues related to the actual constructions of these weak PRFs and stuff, but we do have a section in the paper discussing how we can just get it from the VDLPN assumption.
Yeah. Just rephrasing, I think he's also asking about private information retrieval, like is a potential application of the constrained PRF from inner product. That's what probably he's asking. Like,
sorry, what?
Private information retrieval, like PIR.
Can you get, I don't think you can get PIR from that, no.
Yeah, all right, yeah. So yeah, I mean, just a small clarification. I mean, is it like the public key setup? Like, so what's a particular use case where it becomes really important?
To have public key setup?
Yeah.
So the advantage of public key setup is that it allows you to generate OT correlations kind of on the fly. So I don't have to agree with you ahead of time or even be online with you at the same time to generate.
I see. Yeah. So it makes things asynchronous. That's
it makes things
right?
asynchronous, and also it makes things reusable. So in the paper we show that if you want to do multi-party computation, you can reuse the same key with all the parties, and that improves communication by a lot.
Yeah. Okay. Yeah. So these few OTs are not reusable because you run out of them.
Exactly. And you have to be online and communicate, and it's
okay. Okay. All right. Thank you. So if there is no other, here's a question. Great.
Yeah. Thank you. Nice talk. Sorry if I'm missing, but I cannot see why the Pratyay have to be non-interactive. So could you explain that briefly?
So if the vector OLE is interactive, then we're back to the original case where you need to have, it won't be asynchronous. You wouldn't be able to just post public keys. You'd have to communicate to generate the constraint keys. So actually, this is related to this question of building 2-round OT extension in the random oracle model. It's known that you cannot build 2-round OT extension in the random oracle model in a black box way. You have to have something not black box, but we show that we can just have nearly black box 2-round OT extension using inner product weak PRF. But the point here that I wanted to make is that this is 2 rounds. So if you replace the non-interactive vector OLE with an obliterated transfer, you can get a classical OT extension, basically, where in 2 rounds we generate a few OTs and then we can extend them using quiet OT. Does that make sense?
Yeah. Thank you.
Any other question? If not, we thank Shasha again for 2 talks, so double applause.